So Talya, do you want to go ahead and share your... Okay, well, great. So now we'll have Talya Eden, who will tell us about sampling subgraphs from edges to cliques.
Hi, thanks. Yes, so I'm going to talk about sampling subgraphs in sublinear time, and this is based on joint works with Dana Ron and Will Rosenbaum. Okay, so this is not working. Okay, it is. So let me define the task. We're given query access to a graph G with arboricity at most alpha, and we want to design a sublinear algorithm for sampling a k-clique from a distribution which is epsilon pointwise close to uniform. So it means that for any k-clique in the graph, or any k-clique C in the set of k-cliques, which I denote by ck, we want its probability to be the returned one to be roughly 1 over nk. So 1 over nk, that's the uniform, and we allow it to deviate by a multiplicative factor of 1 plus minus epsilon. Okay, so basically we have this graph G, and we're giving query access to it, and we want to design this button that whenever we push the button, we get a uniformly distributed k-clique. In here, k is 3, and each one as equal probability, roughly equal probability to be the returned one. So I will soon define the query access model and also what I mean by arboricity of a graph. But before, let me spend another second on this definition of epsilon pointwise close to uniform, and why do we care about this definition? So maybe the more standard definition when we talk about distribution, the more standard definition of distance is the total variational distance, or the L1 norm. So this is the definition, right? The distribution P, its distance to the uniform is just 1/2 of the sum over all elements of the mass that P gives this element C minus 1 over nk, right? And the total sum should be at most epsilon. While in epsilon pointwise close, we want that every k-clique, every C in the domain should have probability that the difference between the mass that P gives it to 1 over nk, it's at most epsilon over nk. So the relative distance is at most epsilon. So what it means that when we look at epsilon TVD close, an epsilon fraction of the k-cliques might be ignored, which might be exactly the k-cliques of interest. While in epsilon pointwise close, every clique should have almost the same probability of being returned. Okay, so for example, if I have this graph and we have this small clique over square root epsilon m vertices, so this has at most this has epsilon m edges, right? So if you're looking at epsilon TVD close, an algorithm that only returns uniform edges from this subgraph, from this sparse subgraph, will be epsilon close to uniform. It's allowed to just ignore this k-clique, but say we want to use these edges to then sample triangles, which we'll actually do in our algorithm, which I'll show you in a second. So if we allow epsilon TVD close only, then we'll never see a triangle, right? Because these edges do not participate in any triangles. So we do care that all edges have probability to be returned. Okay, so now what is the arboricity of a graph? It's a measure of sparseness. So this is not the exact definition, but it's equivalent. It's the maximal average degree over all subgraphs. So for any subgraph S of G, its average degree is at most alpha. So if alpha is small, then we know that there are no dense subgraphs and that the graph is sparse everywhere. So this will help us in bounding the complexity of our algorithm. And we know that for all graphs, it holds that alpha is at most square root. Okay, so sorry about this. So why do we care about this family of graphs? About bounded arboricity, it's a very rich family of graphs, planar graphs, exclude minor graphs, real-world graphs are shown to have bounded arboricity, and also preferential attachment graphs, which are used to simulate random, social networks. So having the ability to parameterize the algorithm in terms of the arboricity of the graph gives us improved results for all of the graphs in these families, which have arboricity constant or small, log n maybe, or actually any bound that is any alpha that is smaller than square root m, we gain from parameterizing in the arboricity of the graph. Okay, so what's a query access model in sublinear time algorithms? Probably know, but I'll just mention. So we assume that the graph is too large to be stored locally, so we can only access the graph through queries and answers. So it is assumed that the vertices are labeled arbitrarily 1 through n, and that the algorithm knows n. So actually it can access uniform vertices. And it can also perform the following queries. It can perform degree queries, just ask what is the degree of the ith vertex, or perform neighbor queries to ask the ith neighbor of the vertex v. Okay, and then it gets an answer. Or if I is greater than d of v, if there is no ith neighbor for v, then it just gets some special symbol. Okay, and finally it can perform pair queries in which it asks, is there an edge between these pair of vertices in the graph? So this is the query access. Okay, so now for the high-level ideas, what we're gonna do is we're gonna define an auxiliary graph GK whose edges correspond to k-clicks in G. And then by sampling edges in this auxiliary graph GK, uniformly at random, this translates to sampling k-clicks in G uniformly at random. And to sample edges, we build on a previous algorithm that we already had for sampling edges. And the challenge will be to simulate queries on GK while only being given query access to G. So the previous algorithm we had was given a query access to a graph G, and the output was uniform edges in this graph G. But now we're given a query access to a graph G, and the output is we want to output uniform edges in this graph GK, for which we do not have query access. So this will be the main challenge of the algorithm. And also we'll build on recursive invocations. We start from the query access gives us access to uniform vertices. As I said, we're building on this, we give an algorithm for outputting uniform edges, and then we'll continue to triangles, 4 clicks, and so on until we reach k-clicks. So we'll build on this recursive invocation of this algorithm. Okay, so for some preliminaries, which might seem a bit technical, but they're important later to bound the running time. So we define a total ordering on the graph vertices so that a vertex u precedes v if its degree is smaller, or if the degrees of the two vertices are equal, but the ID is smaller. So we just break ties according to IT. And for k-click C, we let gamma C be its set of neighbors. It's the set of neighbors of its mean degree vertex. Okay, so if this is our k-click, so just a triangle, we look at the mean degree vertex, and this, the set of neighbors of the mean degree vertex, that's the set of neighbors of the k-click. Okay, and also the degree of the click is the same as the degree of its mean degree vertex. And for k-click C, we let its ID be the concatenation of its vertices IDs, so we can also define this ordering, can generalize it to k-clicks. So now we get the total ordering on the k-clicks. And why is this important? We know that when we'll go from k-1 clicks to k-clicks, we know that it means that there's another vertex whose neighbor of all of these vertices of the k-1 click. So when we'll search to extend this k-1 click to this vertex to get a k-click, it's most beneficial to look for this vertex using neighbor queries of the mean degree vertex, right? Just because it has less neighbors, so we get higher probability of hitting this vertex. Okay, so now for the auxiliary graph GK. So in this graph, each k-1 click in G is a node in GK. Okay, so this will be our graph G, and we'll think about k equals 3. So every 2 click in G will be a node. So every edge in G is a node in GK. And for each k-click C in G, there is an edge in GK between the nodes corresponding to the first 2 k-1 clicks of C. So that was a bit long, but we'll just look at our triangle. Okay, we'll look at our k-click, the triangle, and we'll look at the mean degree vertex, and we'll look at the first 2 k-1 clicks of C. So first 2 edges of C. So the first 2 edges will be AB and AC, right? Because they are the ones to contain the mean degree vertex. And then we'll put an edge between AB and AC, which corresponds to this triangle ABC. Similarly, for this triangle ABD, the first 2 edges, if A is still the mean degree vertex, the first 2 edges are AB and AD, and we'll have this edge corresponds to the triangle ABD. And finally, if for the triangle ABJ, if J is the mean degree vertex, then
we look again at the first two edges. So the first two will now be AJ and BJ, and we'll have an edge there. So this is the auxiliary graph GK. And we see that every k-click corresponds to an edge. So if we can sample edges uniformly at random in this graph, and the edges are labeled with the original k-click, then we can output a uniform k-click in this graph. Okay, so also note that for k equals 2, gk2 is just g, right? Because we said each k minus 1 click in g is a node. So k minus 1 for k equals 2, that's just 1 clicks, and 1 clicks are just vertices. And then for each k click, for each edge, right, we have an edge in g2. So we just get the same graph. So as I said, we'll have some recursive implementation of our algorithm, and the base case will just be g2, where g2 is just g. Okay, so we start with edges in the original graph G. Okay. Okay, so that's what I said. The base case will be G2. So let's start with it. So we'll start with a procedure called try to sample an edge in G2. Okay, and this is a previous result I mentioned before from ICALP 19. And the idea is we consider each edge in the graph as two oriented edges. Okay, so these are the vertices, and now we consider each edge UV as two directional edges, U and going from U to V and from V to U. So these are two edges. And I define the set of low degree vertices in the graph. I call it L0. So L0 is all the vertices V whose degree is bounded by some parameter tau, okay, which will be defined according to the arboricity of the graph. And I assume the arboricity is an input to the algorithm. So I get the value alpha, which is a bound on the arboricity of the graph. And then we let E of L0 be the edges originating in the vertices of L0. Okay, so these two edges belong to EL0. They originate in this vertex that belongs to L0. Okay, so now for the algorithm, what we're trying to do is we're trying to start by sampling an edge in EL0. Okay, how do we do so? We query a vertex. So we query a vertex here, and we query its degree. If it's in L0, then we continue. Otherwise, we fail. Okay, and if we succeeded, if we query the vertex and it is indeed in L0, then we sample one of its neighbors, each with probability 1 over tau. Okay, and I will soon show you why this is important. And then we continue as follows. We choose J uniformly random from between 0 and log n, and we start a walk of length J. So if we just query each time we reach vertex, we query one of its random neighbors. This time it's done uniformly at random. So if we hit a vertex V, then we sample its neighbor, one of its neighbors with probability 1 over dv. Okay, and we continue to do so for J steps. If at any point we return to L0, then we fail. Okay, and otherwise we just return this last edge in the walk, okay, which we took. So we did a short random walk for J steps, and why it is called try to, because sometimes we fail, or actually a lot of the times we fail. We fail if the initial vertex we sampled is not in L0, or if at any point we return to L0. So to get an edge in the graph, we'll actually invoke this many times. But I'll leave that discussion for later. So now I want to claim that this procedure returns each edge in the graph with probability 1 over n tau. So let me give you some intuition to why this is true and where this J equals log n comes from. Okay, so as I said, L0 is the set of all vertices whose degree is bounded by tau. And then we let L1 be the set of all vertices whose degree into L0 is more than 1 minus epsilon its degree. Okay, so most of these vertices, these vertex neighbors are in L0. Okay, 1 minus epsilon of them are actually in L0. Then L2, the set of vertices whose degree into both L0 and L1 is greater than 1 minus epsilon their degree. And in general, Lj, the set of vertices whose degree into all previous layers is greater than 1 minus epsilon their degree. So by the properties of the arboricity, we can show that at some point this process will end. And actually there are at most log n layers to any graph which has arboricity at most alpha. By the setting of tau here in L0 to be 2 alpha over epsilon, it is ensured that we can cover all the vertices in the graph in log n layers. And this is where the log n in the algorithm comes from. So now, to continue to the intuition to the claim that each edge is returned with probability 1 over n tau. So first, for an edge in L0, what's the probability that it is returned? It is returned if here we sampled, when we chose j, we just chose 0. And here we needed to sample this edge. So it happens with probability 1 over n tau times 1 over j, which I forgot here, I'm sorry. So the probability we hit this vertex is 1 over n, and the probability we go to this edge and not any other edge is 1 over tau. So this edge is sampled probability 1 over n tau. So what we did is with probability 1 over tau is we gave these vertices here could have varying degrees, right? One vertex can have degree 1 and others can have degree tau. So what we want to do is, because we want to sample uniformly, we want to give all of these edges the same probability to be the chosen ones, regardless of the degree of the originating vertex. So this is why we sample here probability 1 over tau. And then let's look at this edge here, and what is the probability that it is returned. It is returned if we sampled here j equals 1. So we took another step after the first one. And what's the probability that this is the returned edge? It's the probability that we reached, in the first step, we reached this vertex, right? And we could have reached it from any one of its incoming neighbors. Okay, so this happens with probability at least 1 minus epsilon dv over n tau, because each one of its incoming edges gives it probability 1 over n tau, and there are 1 minus epsilon dv such neighbors. And then the probability that we continued just to this specific edge, which happens with probability 1 over dv. We just sample a uniform neighbor of v, and we see where we got. So the probability we got this edge, altogether, it's 1 minus epsilon over n tau. And then a similar analysis shows that for the set of edges starting in L2, we get that each such edge is sampled probability 1 minus epsilon squared over n tau, and so on. In general, it's 1 minus epsilon to the j over n tau. And so we get that all edges are returned with roughly the same probability. We're just setting epsilon we scale it to be epsilon over log n, then we get that this is most minus epsilon. Okay, so this is the intuition for the edges case. So now let's see what we do in order to sample in GK. So we have our base case, and now we want to go from G2 to GK. Okay, so how does the algorithm change? So we want to start with roughly the same algorithm, but we have to adapt because we don't have query access to GK. So first, what changes is this value of tau. It still has this first term, 2 alpha over epsilon, but also it's the maximum between this term and another term that also depends on n alpha, nk, and epsilon, which I'm not gonna get into. And then we start the algorithm, and we start that we wanted to query a vertex in V uniformly at random and query its degree. But now we can't do this, right? Because the nodes of GK, there are k-1 clicks in G, so we don't have uniform access to them. So what do? We recursively invoke the procedure on GK-1. Okay, so at each step we assume that everything works up to GK-1, and now we're doing the additional step of sampling in GK. So we recursively invoke to get a node, a k-1 click, which corresponds to a node in GK. Okay, so I denote it by V0E is because a node here corresponds to an edge in the original graph. And then we also wanted to query the degree, but again, we can't do this. Why? Because the degree of this node here, it's triangles degree, right? There's some edge in G, and it has so many triangles incident to it. So we don't know it, we don't have any query access to it. But actually, the only reason we wanted this degree query is because we wanted to know if our vertex belongs or not to L0. So this is what we want to do. we want to check if this vertex belongs to L0 of GK or not. So we won't be able to do it using a degree carry, but we'll do something else. Okay, so we call this as L0. It means that its degree in this graph is at most tau. And we wanted to query a neighbor V1 or V0, each with probability 1 over tau. So again, we want to do this exact same thing in GK, but we won't be able to do it directly. We'll have to simulate this query. Okay, and here again, we wanted to check belongingness to L0 and to query neighbors in this graph GK. Okay, so the rest, so it's actually the same algorithm exactly as before, but we'll need to simulate all of these missing queries. So let's see how we do this. Okay, so the goal is now to simulate the queries. And once we can do this, we are guaranteed that a uniform edge in GK is returned, or guaranteed that a uniform K-click is returned. So this is actually all we need to do now, is to explain how to simulate these queries. So this is what we wanted to do. We wanted to verify if some vertex, some node in GK belongs or not to L0. And if it does belong to L0, we want to be able to sample each of its neighbors with probability 1 over tau. And if it does not belong to L0, then we want to sample a uniform neighbor of this vertex. So a uniform neighbor, a uniform triangle incident to it with probability 1 over its triangle's degree. Okay, so let me start with this query. We want to verify if VE belongs to L0. So assume now that I'm looking at this node here, VE is of the edge AB. Okay, I want to know if it belongs to L0. So what I want to know how many triangle neighbors does this edge have. Okay, so if I look at it back in G, I'm looking at some edge, and I want to know how many of its neighbors form triangles with it. So back in G, these vertices might have additional neighbors, right, that do not appear in GK. They're really just neighbors in the graph that do not form triangles with it. And what I want to do, I want to verify how many triangle neighbors it has. So the only thing I have is query access to this graph G. What I can do is I can query uniform neighbors of A and G and check using pair queries, do they form a triangle, right? So I just query uniform neighbor, I check for a triangle. If I don't find one, okay. If I do, then it means that I hit some triangle, right? So I hit some neighbor here. Okay, so once I find a triangle in G, I found a neighbor of this node here in GK. So what's the probability of hitting a triangle? How many times should I try this procedure to get a triangle? So what's the success probability of this attempt? Each attempt succeeds with probability the number of triangles AB participates in, right, over the number of neighbors AB has. Okay, because right, if I just sample neighbors uniformly at random, my success probability is when I hit one of the neighbors that forms a triangle with AB. So the number of triangles, this is just the degree of VE in GK over the degree of this edge AB or of A in G. And recall, we now assume that, or actually we don't assume, but all we want to do is to verify belongingness to L0. So if a vertex does not belong to L0, it will have triangle's degree greater than tau. So I can just assume the vertex has triangle's degree greater than tau, and I can be able to verify if this is indeed the case, right? If this means that if I assume that it does not belong to L0, I know that it has at least this many. This is my success probability. So if I repeat dA over tau times, I'll be able to verify. And if I'll be able to succeed in seeing a triangle with high probability. If I don't see a triangle that I know this does not hold, and it means that my vertex belongs to L0. So I just repeat dA over tau times, this experiment of this procedure of sampling uniform neighbors and checking if they form a triangle. Okay, and now that, again, dA is the degree of this edge in G. Okay, so this is what I do. I just repeat this procedure, d of AB over tau times. Okay, if I see triangles, if I see sufficiently many, then I know that I do not belong to L0, and otherwise this vertex does belong to L0. So this is, we are able to, okay, to verify in this time. But actually, this might be too much. So actually, in expectation, when we are looking at an edge in the graph, which is chosen uniformly at random, and we are looking at its degree, then in expectation, by the properties of the arboricity, this will be bounded by alpha. The average edge degree in a graph is at most, with bounded arboricity alpha, is at most alpha. And recall that tau is greater than alpha. It's the maximum between 2 alpha over epsilon and an additional term. So this is greater than alpha. So in expectation, the number of times I have to repeat this process is not too much, is a constant. But the problem is that the maximum might be very high. It might be that I hit some edge whose degree is n. And then I have to run n over tau times, which is kind of prohibitive. So we want to better bound this value in the case that this degree is very high. So assume the degree is greater than square root n over alpha. Sorry, square root n alpha. Okay, this is when I say that a vertex has high degree. Then I know by the way that I assigned the k-clicks, and this is why I cared about always starting from the min degree vertex, I know that also the degree of d here is also greater than the degree of a, which is, so it's also greater than square root of n alpha. So how will I try to sample this vertex? I won't do just uniform neighbor queries because there are just too many neighbors. So this will kind of make my success probability very small. What I'll do is I'll try to directly sample in the graph high degree vertices. So how do I do this? This is what I want to do. I want to sample high degree vertices whose degree is greater than the square root of n alpha with probability 1 over, I'll show you I can do it with probability 1 over square root n alpha. So whenever I sample a high degree vertex, each one is sampled with this probability. So to do so, I have this small procedure of sampling high degree vertices. What I do is I sample an edge x, y, and g uniformly at random using the previous result we had for sampling edges. And if the degree of the first vertex is smaller than n alpha, then I just square root of n alpha, I just fail. And otherwise, I return x with probability square root n alpha over dx. So if dx is greater than square root n alpha, I can do this. This is just some rejection sampling. Okay, and if I didn't, if this failed, right, if the rejection sampling I failed, I just return fail. So for some fixed high degree vertex u, what's the probability that I'm going to return it? It's the probability that I hit any one, right here in the first step, I hit any one of its edges, which happens with each one is sample probability 1 over n alpha. So 1 over n tau, which is roughly 1 over n alpha. So it's du over n alpha. And then the probability that I keep it, it's square root n alpha over dx. So it's square root n alpha over du. I get that each high degree vertex in the graph is sampled with this probability 1 over square root n alpha. Okay, so actually here, my success probability is now number of triangles between the minimum between neighbors and square root n alpha. Okay, so this is, so also the number of repetitions I need to make, it becomes smaller. It's just, now it's the minimum between the degree and square root n alpha. So the expected value is still O of 1, it's still constant, but now also the maximum value, the maximum number of repetitions I have to make, it's bounded by square root n alpha over tau, which will be helpful later on to bound the running time of this algorithm. Okay, great. So we are done simulating the first query, the query that helped us to understand if a vertex belongs to L0 or not. So we have two more queries. We want to, if a vertex does belong to L0, we want to sample one of its neighbors with probability 1 over tau. And if it does not, we want to be able to sample it with probability which is uniform over its neighbors. Okay, so let me start with the second task. So this is what we had before. So now it will be very similar, but now we want to sample a neighbor, and we assume that, first we assume that this vertex, this node that we're looking at does not belong to L0, okay? So we know that this inequality holds, right? We know that it does not belong to L0. Its number of triangles is greater than tau. So actually everything same as before holds. So if we repeat these many times, we know that with high probability, we'll see a triangle. So we just repeat everything we said before at most these many times. And then the probability, with high probability, indeed the triangle will be sampled. And also, since each triangle is equally probable to be the sampled one, then each specific triangle will be sampled probability 1 over dgk of VE, right? This is just the number of triangles. Because we just did uniform neighbors and then checked for a triangle, no one particular triangle gets more weight than another. They're all equally likely to be returned. So it means that each one is returned with probability 1 over the number of triangles. And this 1 plus minus epsilon is due to the way we sample high degree neighbors. They have some, it's not exactly 1 over square root and alpha, it's 1 plus minus epsilon. So we have this 1 plus minus epsilon here. But roughly, we get that we can sample each neighbor with equal probability, which is what we wanted. So we are also done with this query of a neighbor query for a vertex in L0. And the final query that we need to simulate is for the case that that VE does belong to L0. Okay, so now this is no longer the case. We don't know that the number of triangles, the degree of VE in GK, it's no longer greater than tau. It can be actually very small. So it might be even 1. But we don't want to repeat this term over 1. That will be too expensive for us. This is the only budget that we have. Okay, this is what we are allowed the number of repetitions we are allowed to make in order to keep the budget. But this is actually okay, because recall all we want now is for each neighbor to be sampled with probability 1 over tau. So this actually holds if we repeat this many times. So let's see why. So what is the probability that we repeat these many times and we do not sample a neighbor? This is the probability. In each attempt, in each single attempt of sample a neighbor and check if it forms a triangle, this is the success probability. It's the triangle's degree of this node over this minimum value, right? So the probability we do not sample a neighbor, this is 1 in a single attempt, it's 1 minus this term. And the probability we do not sample a neighbor in these many attempts, right? It's just this expression, right? It's raised to the power of the number of attempts. So the probability, so 1 minus x to the y, it's roughly 1 minus xy, right? So we just get this is the probability that we do not sample a neighbor, right? These two terms cancel. See, we have the same term here and here. These two terms cancel, and we just get that the probability we do not sample a neighbor is 1 minus the degree, the triangle's degree of this edge over tau. So the probability we do sample a neighbor, it's the triangle's degree over tau. And then, since each neighbor is sampled with equal probability, again, no one triangle gets more mass than another. They are all equally probable to be the sampled ones. It means that given that we sampled an edge, which happens with this probability, right? So given that we sampled the triangle, which happens with this probability, each one of the triangles is equally likely to be the returned one. So each specific neighbor is sampled with probability 1 over tau, which is exactly what we wanted. Okay, so we managed to sample a neighbor, and if a vertex in L0, each one is sampled with probability 1 over tau. Great, so we actually implemented this algorithm in GK using simulations in G, and by the correctness of the algorithm in G, right, the correctness it has on edges, we know that we return a uniformly distributed edge in GK, which is a uniformly distributed k-click in G. So to see what we get, what is the running time, so each specific k-click in the graph is returned with probability 1 over n alpha times tau to the k minus 2. So the first 1 over n alpha is from the probability of seeing a specific edge. And then we lose a factor of 1 over tau in each recursive invocation, the same as we lost this alpha factor in the first, in the edge case, okay? Because we sampled the first edge in the walk with probability 1 over tau, we lose a factor of tau in each invocation. So this is the success probability of each specific k-click. So the overall success probability of a single invocation, it's just the number of k-clicks over this term. It's nk over n alpha tau to the k minus 2. Also, the cost of a single invocation, as we saw, it's the minimum of DE and square root n alpha over tau, where E is a uniformly distributed k minus 1 click in G. And by the properties of the arboricity, for every k click in the graph, its average degree, if I take this an expectation of this expression over all k minus 1 clicks, which are chosen uniformly at random, I get that it is bounded by alpha over tau, okay? Just because the mean degree of a k click in the graph, the average mean degree, it's at most alpha. So you get alpha over tau, which is O of 1. And the maximum cost of an invocation is square root n alpha over tau. So the overall complexity is therefore the maximum over the expectation. I can show that with high probability, this is the overall complexity. It will be the number of repetitions I have to make, right? Because this is the success probability of a single invocation. So this is how many invocations I should take in order to successfully hit a k-click, plus the maximum value of a single invocation. So if I set tau to equate these two, or tau prime to equate these two terms, this square root n alpha over tau, this term, I get, and I take tau to be the maximum between this and alpha, because I must have tau greater than alpha for the edge analysis to go through. I get this very terrible expression, but still it is the right expression. So I actually have 2 more minutes. I can show you a matching lower bound. So this is what I get just by equating the two terms, finding what the value of tau should be, just plugging it back in. Okay, and then taking the maximum between that and alpha. And also there's this minimum n alpha here, because always I can just read all the edges in the graph using n alpha queries, kind of download the graph. I said it's stored somewhere remotely, so I can just download the graph and then do local computation. So I never need more than n alpha queries. Okay, so this is the expression we get. It doesn't give much intuition, but maybe let me show you that there's a matching lower bound for this term. Okay, so this is the term that we get from setting tau here, as I said, and if this is the maximum, this tau here, not alpha. And this is the expression I get if alpha is the maximum between these two. And okay, so let me show you the lower bound. How do we get it? We start from a graph G prime that has n vertices and n k clicks. Okay, so this is just any graph that has these properties. And we add to it a complete bipartite graph with sides of size n and square root n alpha. Okay, so on the left we have a set of n vertices, on the right set of square root n alpha. So it's not a complete bipartite graph, I'm sorry. So it's just a bipartite graph. Here all the vertices have degree alpha, and here all the vertices have degree square root n alpha. Okay, so we can verify there are n alpha edges originating in this side and n alpha edges here. So it's not a complete bipartite graph, I'm sorry. So also it can be verified that this graph is arboricity at most alpha. Okay, because just this is the subgraph that maximizes the average degree, and the average degree here is alpha. Okay, and then what we do is in this bipartite graph, we hide a click. Okay, we hide a click. We hide our k-click here among the set of high degree nodes. Okay, so all of these nodes have degree square root n alpha, and we hide the click between these vertices. And let's see what's the probability of hitting this click. So to hit the click, you must first hit one of its edges to realize you're inside this click, right? Because so you must hit some two vertices in this set that both have the high degree. So the probability of hitting this edge, there are n alpha many. Say you are given a budget of q queries, or actually k q queries. So if you spend the first q on trying to see this edge, the probability of success is q over n alpha, because there are n alpha many pairs here. If you just sample them uniformly at random, that's the best you can do to find this edge. So the success probability is q over n alpha for the first edge. And then once you've seen this first edge, to continue to reach the other vertices, it gets easier, right? Because now it's better to just look for inside the neighbors of this set, of this vertex, right? We just do uniform neighbor queries and then a pair query. So now the probability of hitting subsequent vertices, it's q over square root of n alpha, right? Because this vertex has square root n alpha neighbors. So if I sample them uniformly at random to kind of to hit the right neighbor, it happens with probability q over square root n alpha. So in total, to output this hidden edge, I must, this is my success probability. It's q over n alpha, and then q over square root n alpha for k minus time times, right? Because I first saw an edge, so I'm missing k minus 2 additional vertices. So it's just q to the k minus 1 over n alpha to the k minus 2. Okay, and if I say that this probability must equal 1 over nk, right? Because I want this k-click to be returned with equal probability, with uniform probability, then we get that q is omega of this expression, right? We just move n alpha here and take the root of 1 over k minus 1. So this is the expression we had before. So despite the fact that it looks kind of artificial, this is actually tight. Okay, and maybe just to mention some related works. So actually the second expression here, it's also the complexity of counting k-clicks. So for edges, we had that sampling edges, that counting edges and sampling edges, the two separate works, they have the same complexity. But as we saw now from this lower bound, that actually we have, for k-clicks, this is no longer the case. There's a separation between counting k-clicks, which this is the complexity, but never mind all the terms. You can see this, this is the meaningful term, and alpha to the k minus 1 over nk, which also we have it, but we take the max between this term and another term. So actually counting k-clicks could be done more efficiently than sampling them. Maybe it's not very surprising because in counting, we're allowed to ignore an epsilon fraction of the k-clicks. And as I said, in uniform sampling, in pointwise close to uniform sampling, I'm not allowed to ignore any k-clicks. So maybe much more surprising is that actually for edges, it's the same complexity. Maybe I found this very surprising when we saw this algorithm, but indeed for k-clicks, this is no longer the case. So that was it. Thank you.
Thanks, Talya. So
If there are any questions, I'm happy to answer here or later.
okay, so I'll guess we can take a break. I think we'll be back at 10:30. And yeah, feel free to hang out at the Gather Town. And then Alex Wine will tell us about low degree hardness of random optimization problems. Okay, so see you guys soon.